Yeah?
Yeah, just.
Okay. Alright, so good afternoon everyone. So the main goal is to prove the ELP theorem. But before we do that, we need to finish the proof of this lemma that we did not finish last time. So we'll do this again. Right, but we have proved these results. Right, and right, so this lemma is about Dulmage-Mendelsohn barrier. So let's just remember, let's just recall what a Dulmage-Mendelsohn barrier is. This is for a matchable graph. We want the core to be matching covered. And we want all the odd components of G minus B to be critical. Each odd component of G minus B is critical. Yeah, these are the two properties we want for Dulmage-Mendelsohn barrier. And we have already shown that inside any maximal barrier in a matchable graph, there exists a Dulmage-Mendelsohn barrier. So inside every maximal barrier, for sure there is this creature. Okay, so it could be equal to the maximal barrier, or it is a proper subset of the maximal barrier. Of course, it is non-empty because the code is matching covered. So definitely, by definition, Dulmage-Mendelsohn barrier cannot be an empty set. Yeah. Okay. So everybody agrees that we have proved these results 1, 2, and 3. So we are now at 5.4. So what does this statement say? Let's make a drawing. We have a matchable graph. And we have a certain cut. This cut is an even cut, unlike most of the cases where we deal with odd cuts. Sometimes in life you have to deal with even cuts. So this is your partial x. Let's say this is the x side and this is the x bar side. We know that the graph induced by each shore is connected. Both of these graphs are connected. The graph G itself need not be connected. However, we know that, well, the statement is that if the edges in this cut are unmatchable, if all of the edges in this cut are unmatchable in the graph G, then there exists a Dulmage-Mendelsohn barrier such that the barrier and all of the corresponding odd components, they are all inside one shore. They'll all live on one and the same shore of this cut. Yeah. So what we want is a drawing like this. We want a barrier and all the odd components live here. This is what we want. Yeah. Okay. So we'll do this part again. Right. So we dealt with one case that was an easy case. Supposing this cut is actually empty. That means the graph is actually disconnected, if and only if, right? So if partial of x is empty, well, note that both the graphs are matchable because the whole graph is matchable and these edges are not matchable. Therefore, both of these graphs, G induced by x and G induced by x bar, this is irrespective of empty or not. These two graphs are matchable. And by hypothesis, they are also connected. So because this is a matchable graph and there are no edges here, I will just take a Dulmage-Mendelsohn barrier in this graph, which we know exists by Lemma 5.3. Take any maximal barrier, inside that lives a Dulmage-Mendelsohn barrier. So I'll just take a Dulmage-Mendelsohn barrier here. So I'm just dealing with the left graph. ignore the right side. And now observe that since there are no edges going from here to there, this is a Dulmage-Mendelsohn barrier in the whole graph as well. Yeah. This part will just be an even component after deleting B. So even component has no effect on the core, and of course the odd components are still critical because they are critical here. Yeah. So this just goes through. If the cut is empty, easy, and fill it yourself. I'm not going to write it down. We will deal with the non-trivial case where there is an edge in the cut. So now suppose there is an edge in the cut. And let UV be one such edge. Let UV be an edge in partial x, edges notation. So that U is an x and V is an x bar. Maybe I should call it E equal to UV. There might be more such, there might be parallel edges for all I know. Okay, fine, better. Yeah, so this is our edge. We want a Dulmage-Mendelsohn barrier such that blah blah blah, right? It lives itself and all the odd components live in one shore. We know this edge is unmatchable by hypothesis. All these edges in the cut are unmatchable. So we will do what we normally do. We will take a barrier containing the two ends of this edge. Right? It's unmatchable, so there is a barrier containing both ends. So therefore there is a maximal barrier containing both ends, because we want to use Lemma 5.3, which says that inside a maximal barrier you can find a Dulmage-Mendelsohn barrier. Right? So by let V star denote a maximal barrier of G such that U and V are both in B star, and by Lemma 5.3 there exists a Dulmage-Mendelsohn barrier that lives inside B star, that is a subset of B star. There exists B subset of B star. Clearly B cannot be empty such that B is a Dulmage-Mendelsohn barrier. Well, because it is a Dulmage-Mendelsohn barrier, it can be empty. Okay? Yeah? Because the empty set is a barrier, it's just not Dulmage-Mendelsohn. Okay. So we took B star. Let me draw B star. Hopefully I have a much better understanding of this proof than last time. So we'll see how it goes. Let's say this is my doesn't have to be this big. Then my B star. This is the edge E. These are the two ends U and V. Inside this, we have a Dulmage-Mendelsohn barrier. Of course, it could be equal to B star for all we know. And we have some odd components and even components after deleting B star from G. The first thing we will show, which is what we started last time, we will take an odd component and we will argue that the entire odd component either lives here or there. It can't have some vertices in X and some in X bar. That's the first thing we'll show. And actually we did discuss that if we show that we are done. Right. So, but let's just show this. Maybe I'll use blue. Claim. For any component, odd component, let K be an odd component not of G minus B star but of G minus B. This is what we care about. We want a Dulmage-Mendelsohn barrier with this property. Right? We don't care about the barrier B star, we care about B actually. But we will also use the some properties or facts about B star to make some conclusions. So let K be any odd component of G minus B. Then the claim is that the vertex set of K is either completely contained in X or it is completely contained in X bar. Yeah, this is what we want to prove. X and X bar are actually even cardinality sets. So if it is completely contained in X or X bar, it will actually be a proper subset. It can't be equal because vertex set of K is odd number of vertices. So I can make this stronger. Yeah, it will be a proper subset of X or it will be a proper subset of X bar. Well, suppose not. Suppose there is an odd component that violates this. Supposing this is my odd component that violates this condition. By the way, at some point Mr. Samuel will come to give us the key. I don't know, maybe we will. Anyways, suppose not. So K has some vertices here and some here, and I will adjust notation like I did last time, but Lucchesi-Murty reverse it. So I will assume this is odd number of vertices, this is even number of vertices. So let's suppose here we have odd number and here we have even number because the total number of vertices in K is odd. Yeah. Adjust notation so that vertex set of K intersection X is odd, therefore the other is even. And what I started doing is I started arguing things over here. We will argue things over there. We will argue things in the even side. Okay? I would like to convince you that this K, this part of K which is in X bar, notice that it is an even number of vertices. X bar itself is an even number of vertices. So they could potentially be equal. This even set could be the whole even set X bar. We don't know right now.
Proper subset.
That's the point, yeah. That's right. But the point is B star, this is where we are going to use a fact. K is also an odd component. K is also an odd component of G minus B star, part of Lemma 5.3, second part. The odd components of G minus B are also components of G minus B star. Right? Because without that I don't know whether there are some vertices here that are not here. You get the point. But because K is also an odd component, after deleting B star, and B star contains a vertex in X bar, in particular the vertex V. Therefore, this vertex is a vertex in B star that is not here. You all agree? Yeah. B star intersects both shores, and K is an odd component of G minus B star. Therefore, vertex set of K intersection X bar is a proper subset of X bar. Okay, let's use. Since B star's intersection with X bar is not empty and K is a component of G minus B star as well, I claim that the vertex set of K intersection X bar is actually a proper subset of X bar. In particular, V is a vertex that is here, but it is not here. Yeah. Okay. Yeah. So therefore, this blue part is a proper subset of this part. That is what we have concluded. This shaded area is a proper subset of this entire set. They cannot be equal sets. Yeah? Okay, good. Questions? Yeah?
It is an odd component of G minus B star, right?
Right.
It's not any component.
Yes, it is an odd component. That's right. Yeah. Yes, that's right. Yeah. Yeah, the reason I put this in odd, because if I just say it's odd components of G minus B are also components of G minus B star. Odd follows because it was an odd component to begin with. Yeah, that's right. Yeah, you're right. It is actually an odd component of G minus B star. Yeah, good. Everybody with me? Yeah, you all agree that this is a proper subset of this entire part. But now we will use the fact that this is a connected graph. Since the graph induced by X bar is connected, there is an edge that goes from this set to the outside. There exists an edge F with one end in this part, vertex set of K, intersection X bar, and other end in X bar minus the vertex set of K. You all agree? There is an edge that goes from here to the outside. Where can it go? If that edge goes from the odd component K to outside, that other vertex also belongs to B star for sure, but it also belongs to B. Because this is an odd component of G minus B, all edges from the odd component can only go into B, since it is a component. Right? So the other end, not only does it belong to B star, it actually belongs to B. This implies that the other end lies in B as well. So we concluded that B also has non-empty intersection with the X bar part. This is something we did not know. We knew that B star has non-empty intersection because the vertex V belongs to X bar and it belongs to B star. But now we concluded that B also has some vertex that is here in the X bar part. Other end lies in B. Right? And B, if it lies in B, it also belongs to B intersection X bar, because the other end lies in X bar. This is the same end. I am talking about the same end over here. Yeah. So what we have concluded is there is an edge that goes from here to some vertex. This is the edge F, and this vertex belongs to B as well. It could be equal to V, I don't know. But it is a vertex that is in X bar and it is also in B. Everybody with me? Questions, concerns? Therefore, this is an edge of some graph we like. Core. With respect to B. This edge F is also an edge of the core with respect to the barrier B. Yeah. Note that F is an edge of the core with respect to B. And if you have an edge of the core with respect to a Dulmage-Mendelsohn barrier, then what can you say about this edge? This edge is matchable in G as well. Everybody agrees? This edge is matchable in G. This is lemma 5.2. Right? By 5.2, F is matchable in G. TIY, try to get a contradiction from here. See if you can figure out a contradiction from here. And if you have figured out something, raise your hand, I'll come and talk to you. Yeah? Everybody sees it? The main point is to get a contradiction to something in the hypothesis. We know that all the edges in the cut are unmatchable in G. Consider the perfect matching or a perfect matching of G that contains the edge F. Consider any perfect matching of G, right? This is the main statement. F is matchable in G. So there is a perfect matching MF containing F. MF is a perfect matching of G containing F. And now just do some counting, right? So we'll use which color? Yellow is fine. So we are taking this edge. This is we are looking at G. We have a perfect matching containing this edge. This had an even number of vertices. After matching this outside, I am left with an odd number of vertices here. But that odd number of vertices has to match, some vertex will have to match to some other vertex outside this set. Where will that other end be? Right? This is an odd component after deleting the set B. Right? And one vertex is, if you think about, maybe draw with respect to a barrier, we know what any perfect matching looks like. This is SGT assignment 5. With respect to a barrier, every perfect matching looks like this. And even components have a perfect matching. Every perfect matching of a matchable graph basically looks like this. So I have already used this edge going from K to the barrier B. This is my B and this is my K. So therefore the rest of K has to be matched within itself. That's how barriers work in matchable graphs, right? So therefore there will be some vertex here that is matched here. But these edges are unmatchable in G. So therefore we have a contradiction. Right? So what we have proved is this claim. Right? So I'll just say claim QED. Right? The claim has been proved. Every odd component of G minus B either lies in X or it lies in X bar. This is done. Right? And just for the sake of completeness, let us also see why this claim is the only thing we needed to prove. Once we prove this claim, we have proved the statement. Right? This is something we observed last time. So let's see. Okay, fine. Once the claim is proved, let's see a drawing. So I'll repeat this drawing here. This is my graph G. This is my X bar. This is partial of X. And we have a Dulmage-Mendelsohn barrier. And we have these odd components. What we know about the odd components is that they look like this. Either it is completely here or completely there. And the Dulmage-Mendelsohn barrier, I don't know what it looks like, but it could have some vertices here, some here, maybe one of these sets is empty, I don't know. The point is, because I am assuming that some odd components are here and some are there, or let me put it this way. Think of the core. Right now what you can do is you can think of the core. If the entire core is not on one side, that means that some edge of the core belongs to partial of X. If the entire stuff does not lie here or there, that means that some edge of the core will belong to the partial of X cut. But those edges of the core are matchable in G. Therefore, the entire core has to be here or here, which is what we wanted to prove. Right? So once we prove that the odd components are contained inside X or inside X bar, the rest just follows. Right? Okay? So therefore we are done with Lemma 5.4. Everybody convinced?
I have a question.
Yes.
So if I say that the core has to be within G induced by X or X bar without proving the claim, what is the gap there?
I see. You are saying that, yeah, what is not clear is the following situation maybe. So maybe I'll draw it here. So if we don't prove this, something like this could happen. Yeah, so I think I see your point. What you're saying is, why did we need to prove this claim at all? Couldn't we just have used this kind of argument to finish the whole thing? Yeah, that's a good point actually. So why can't this happen? Why can't my entire barrier be here? And I will just draw one odd component like this and the others like this, just for the sake of getting a nice drawing. And maybe all the edges of the core, they don't go from here. They, for this component, they all go from here.
Yeah.
There are all the edges here. This could happen, right? Yeah.
Yeah, makes sense.
Or can it not happen?
Yeah, maybe there's a way to argue it can't happen, but again.
Well, I mean, then this has to be the entire x bar. Right? Because if this is not the entire x bar, then because this is a connected graph, some edge has to go somewhere, but the entire barrier has been drawn on this side. So maybe in this case, this has to be the entire x bar. So maybe there's another way to prove it, where you first use this kind of argument to arrive at some conclusion, and then you argue further to say that the whole odd component has to be. Of course, I could have made this more messy. I could have put two odd components like this, and all the edges go like this, right? So, yeah. So one needs to work with this situation. This is a problem. Because this is a connected graph. So two odd components cannot happen. Yeah, good point. So this doesn't happen. Yeah, okay. So this could still happen. Yeah. But yeah, maybe there is another way to prove, where you use first this kind of argument and then you deal with this situation. Yeah. Okay, good. Alright, questions, concerns regarding Lemma 5.4? Everybody's convinced that we proved it? Yeah? We didn't really use the hypermatchability explicitly anywhere, did we? I mean, it's a bit weird because, of course, we took the Dulmage-Mendelsohn barrier inside a maximal barrier containing the vertices u and v. So the odd components are hypermatchable. But it's not clear how we explicitly use the hypermatchable property. That is not clear.
What was the actual assumption of this? What's on those So the way we took the first barrier,
yeah.
When we look at the endpoints of that edge, and we took a barrier containing that.
Right.
Right. And then we said that what if there exists this kind of a component
right.
in V?
Yeah.
So then we proved that there will be an edge from like this side of this to that existence of that edge.
Yeah, that's right, yeah.
So I just want to understand like what he said about this barrier. How can this be on the one side thing?
So what I meant was take any Dulmage-Mendelsohn barrier directly instead of taking these stuff first.
Yeah.
Then it has to be on this side.
So you are trying to use this kind of argument first, that the entire core has to be on one side because the edges of the cut are not matchable. Right. Yeah, that is I think what Santosh was trying to do. Yeah. So yeah, maybe there is a way to proceed like that and then finish the proof from there. Yeah. Okay. Good.
Is it
yes.
easy to see from 5.2 that entire core will, core will be, barrier will be, DM barrier will be in one side? Because that crossing is
yeah. Wait. If the entire barrier is not one side, then the barrier itself is split, supposing. Then you will have some edge. You take an odd component.
connectivity and
Because of connectivity, it should follow.
matchable also.
Yeah. Because the core is a connected graph. It is a matching covered graph. Therefore, it is connected. It follows that the barrier itself has to be one of the two sides. Yeah, that's right.
And in that case, this entire core, this core components will also be in one.
No, this is the only issue, right? This is not clear.
After this claim, I'm saying.
After this claim, yes, that's right. Yeah. So this is the only thing that we need to resolve, which is what this claim does. Yeah. Okay. Good.
And that A from that odd component to barrier is due to that cut is non-empty.
Right. If things are split, if the core is not completely on one side or the other side, then you will definitely have some edge because it's a connected graph. The core is a connected graph. So every cut, think of this cut with respect to the core. Right? Some edge of the core will belong to this cut. Right?
Core is matching cover to connect.
Therefore connected. Exactly. And that will be a problem. Yeah. Yeah. Okay. Good. Alright. Any other questions or concerns? Yeah. Everybody's okay with Lemma 5.4? Okay. So then we are done with Lemma 5.4, which is the only last ingredient that was remaining for the ELP theorem. So now we are ready to start proving the ELP theorem. Right? Okay, so I'll erase the proof, but I will keep all the statements. Okay. Is this 5.7 maybe in the book, is it? Does anybody have the book? I think it's 5.7. Doesn't matter. Huh? 5.6. Huh, thank you. What is 5.5? Or maybe it is a claim inside the proof of 5.4. Okay, so what does the theorem say? The theorem says that every matching cover graph that has a non-trivial tight cut has an ELP cut. What is an ELP cut? I don't know what Lucchesi-Murty used, but I am going to use the following definition. It is a non-trivial barrier cut or a two separation cut, which is non-trivial by definition, the way we defined it. Okay. So as we discussed earlier, this was proved by Edmonds-Lovász-Pulleyblank in 1982 using LP duality. And the first graph theoretical proof was by Zoltán Szigeti, 2002. And in 2018, if I am not mistaken, Carvalho-Lucchesi-Murty gave an alternative proof that was inspired by many of Zoltán's ideas, but it is somehow more closely tied to the theory of matching covered graphs. Even then you can see you have to sometimes go into matchable graphs. So these lemmas are going to be useful. Right? So we can't, we don't know any proof that basically deals only with matching covered graphs. Somehow we are forced to deal also with these annoying matchable graphs. So we will see CLM's proof, which is basically what is there in the book, perhaps an even simplified version in the span of another 6 years or so. So, proof. So let's say G is your matching covered graph that has a non-trivial tight cut. So it's neither a brick nor a brace. Let's first make an observation. If the graph is not bicritical, then we are done. Let's see why. If it is not bicritical, maybe you all can think about it. DIY. Think about it and raise your hand. So here is a quick DIY. If G is not bicritical, then we are done. There is some technical detail to be figured out, so see if you can figure it out. Make a drawing. Helps a lot. Today you want something. Anybody else? You can keep it. Or maybe give it to them. Thank you. Make a drawing. If it is not bicritical, what can you say about the graph? Anybody else? Right, so if the graph is not bicritical, then there is a non-trivial barrier. If there only is, right? So just make a non-trivial barrier and think about definition of barrier cut. Right? So you have a non-trivial barrier. Let's say it has 5 vertices because 5 is as good as any other number. Then you have 5 odd components. If any of the odd components is non-trivial, then you all agree we are done. If any odd component is non-trivial, we are done. If all odd components are trivial, then the graph is bipartite. We've already characterized tight cuts in bipartite graphs completely. All non-trivial tight cuts, or rather all tight cuts in bipartite graphs are barrier cuts. So in both cases you are done. Right? Yeah? Okay? So this is easy. Either you get a non-trivial barrier cut or you conclude the graph is bipartite and again you get a non-trivial barrier cut. So this is going to be very crucial. Let us call it star. Whenever we conclude that the graph is not bicritical, we just call star and we finish. Yeah? Okay. Alright. So this will keep happening throughout this proof. But now we actually start the proof after this observation. Right? So I'm not going to write assume G is not bicritical or bicritical. I'm not going to write it. This is just an observation. If the graph is not bicritical, then we are done. Okay, fine. Now let's begin the proof. We will choose a peripheral tight cut. No. We don't need peripheral tight cut. We will choose a tight cut that has the property of lemma 5.1. We will choose a tight cut that has an edge such that if you delete the corresponding end from the corresponding shore, graph is still connected. That is what we proved in lemma 5.1, that peripheral tight cuts have this property. In the proof, we don't need the cut to be peripheral. We just need a cut with this property. So let's write down. Let C partial x be any non-trivial tight cut that contains an edge E UV where U belongs to X and therefore V belongs to X bar, such that both graphs induced by X minus U and graph induced by X bar minus V are connected. By lemma 5.1, such a cut exists. In particular, you can take a peripheral tight cut, it will have this property. But in the proof, we are not going to take a peripheral tight cut. We are just going to take this second property. Yeah. So exists by 5.1. Let's make a drawing that is much more useful. So let's see. So this is my graph G. This is my cut. This is a tight cut, non-trivial tight cut. I wrote non-trivial, good. It's a non-trivial tight cut. And it has this edge. I'm going to draw this edge here. E U V. This is the X part. This is the X bar. Sure. Yeah, this is our graph. And what this statement is saying is that, of course, we know that every tight cut is a bond. We know that the graph induced by X and the graph induced by X bar, we know that they are both connected. But what this is saying is that even if you delete this vertex from X, you will have a connected subgraph induced by the remaining vertices, and same for V with respect to X bar. Yeah, you okay? We'll probably take a break soon. Yeah. Yeah, okay. We'll try to finish one case here and then we'll take a break.
How we can claim that such a cut exists?
Peripheral. We know that peripheral tight cuts have this property.
But we don't know that matching covered graph has a peripheral.
There's always a peripheral tight cut. Think about the definition of peripheral tight cut. Right? If partial x is not a peripheral tight cut, then I then take a subset of x that is
Oh, okay.
right. So
I can go down.
yeah. So there is always a peripheral tight cut.
Yeah.
Right? Yeah. So yeah. Okay. So therefore, such a cut exists. Yeah.
Maybe leftmost in the laminar family.
Exactly. Take a maximal laminar family and take leftmost, rightmost, whatever. That works. Yeah. Exactly. Yeah. Yeah. Okay. Good. So we have this situation. We have this. Okay. So we'll consider two cases. And inside one of the cases, we'll consider three more cases. Okay? The easy case is the following. The only neighbor of u in x bar is v, and the only neighbor of v in x is u. That's case 1. Okay? Let's write down. Case 1. The only neighbor of u in x bar is the vertex v, and the only neighbor of v in x is the vertex u. Yeah? This is one case we'll consider. And we'll finish this case and then we'll take a break. So the idea of the proof is that in most of the cases, except for one case, total there are 4 cases. Case 1, case 2, point 1, point 2, point 3. 4 cases. Right? So case 2 is not case 1. That is clear, right? Case 2 is not case 1. Good. Except for one case, which is going to be the last case, we will basically argue that the graph is not bicritical. We will call star and we will finish the proof. Right? So, in order to conclude that the graph is not bicritical, we will go to another graph which has the properties that are stated in the hypothesis of Lemma 5.4 that we just proved. Okay? So we will go to a graph that is matchable and it has this cut. Both the shores should induce connected subgraphs. That is where this will somehow come into the picture, right? And we want that no edge in the cut is matchable in the graph, in that graph. Of course, in the graph G, every edge is matchable. But in that graph, it's not matchable. Right? That is where we use the fact that this is a tight cut. Because this is a tight cut, we will get this property that is in the statement of Lemma 5.4. And then we will use the conclusion, we'll get a Dulmage-Mendelsohn barrier in that graph with nice properties, as you can see here. And we will use that Dulmage-Mendelsohn barrier to show the existence of a non-trivial barrier in the original graph G. But if there's a non-trivial barrier, then it is not bicritical and you are done by star. In one case, we will not be able to do that because there exist bicritical graphs. Right? So in some case, we should not be able to do this. And that is the case where we will show that there is a 2 separation. Therefore, there is a 2 separation cut. Yeah? Okay, that's the general philosophy of the proof. The strange thing in the proof is the specific matchable graphs that we will look at. One of them is not so strange. One of them is exactly what you think. We will delete u and v. This we already discussed last time. We will take g minus u minus v in this case. Consider g prime to be g minus u minus v. This case is easy. In some sense, this is intuitive. You delete these 2 vertices and now observe that g prime satisfies the hypothesis of Lemma 5.4. DIY, quick. DIY, check that g prime, what is the cut? Well, the cut is exactly this cut after you forget these two vertices, partial of x minus u. Check that G prime with partial of x minus u in G prime satisfies the hypotheses of Lemma 5.4. Check. Once you're done, you can raise your hand. We'll wait for everybody to raise their hands. Yeah. Even if you checked it last time, check it again. Wait. If you are done with this DIY, here's your next DIY. Apply Lemma 5.4 and complete the proof. Conclude that the graph is not bicritical. Conclude that G is not bicritical. If you do both of these, this case is finished. Okay, when you are done, let me know. Raise your hand, I'll come and talk to you. Yeah, looks like I got the numbering wrong. I'll correct that. This is 4. This is 5. Okay. This is okay. This is okay. Okay. Yeah. You're looking at or U? This is on. I forget. I thinking that this is. But now we have to add.
The Dulmage-Mendelsohn variant that can that be trivial?
Right. Good.
Yes. Still,
Yes. That's right. Yeah.
so I get one here. Every rigid partial x has to be incident with either B or U because these are components.
Yes.
Then I just add U and this is one more odd component.
Yeah, if you convince me that those odd components are odd components, I don't care about the last one. In general, if you give me k vertices and you tell me there are k minus 1 odd components, I will not care about the last one.
Oh yeah, that's right. Yeah. But yeah, if I add this to U, it's still these are still components.
And you're using some hypothesis there.
Everything's coming.
You're using something in the case. If you're not using the case, then you have proved for all cases. You have to use the case. If you have an argument that doesn't use the hypothesis of the case, then you have proved all cases. That's a problem. Because there are bicritical graphs. Right? So somewhere you have to use the case. Yeah.
This is the part.
Right.
Many other VUC.
Yes.
But the other case I'm not using, but technically I am because I
Yes,
don't
you
know
are.
where
You are just a notation.
yeah, where the damage is.
I don't care about that. If you give me k vertices and you give me k minus 1 odd components, I will stop thinking. Okay? Anybody else? And you make sure that you're using the case.
Yeah, because if I'm adding this inside this, and the only neighbor is G. So this G x bar is going to be a connected.
I don't care about that. If you just convince me, supposing there are 4 vertices here. Now you're adding one more vertex. Convince me that there are 4 odd components.
4 or 1 component.
Yeah. If you convince me that, then I don't need to care about the last component.
The last component.
I don't care. In general, if you give me k vertices and you tell me that after deleting these k vertices, there are k minus 1 odd components, I don't care about the last odd component. It exists because there can't be k minus 1 odd components. Parity. So yeah. So just try to convince yourself that there are k minus 1 odd components after deleting k vertices. And k is non-trivial, at least 2. Yeah. Draw. Make a drawing first. Supposing it is matchable. No. After you delete u and v, even number of vertices. But x minus u is even. X was odd. X was odd, no? It is a tight cut. Partial of x is a tight cut.
Okay, then that's. I also match.
Yeah, so we looked at even cuts for some time, but now I have drawn an odd cut, and my drawing has no information to tell you whether a cut is odd or even, because I just draw a box. what's the next one? I'll apply Lemma 5.5. Okay. Give it a name B prime. So this is in G prime. Okay. B prime is the Dulmage-Mendelsohn barrier in G prime, and you are putting everything on the x minus u side. Yeah. That's okay. Okay.
So we take this G.
Yeah.
This name.
Yeah.
And this take U and something from here. So we need to decompose it.
So you want to show me non-trivial barrier in G. So you are B prime in G prime. Now how do you make your non-trivial barrier in G? You're almost there. So you have B prime. It's Dulmage-Mendelsohn barrier in G prime. Now if you give me non-trivial barrier in G, then you're done. Then it is not bicritical.
Add U.
Okay. Convince yourself why this is barrier. Somewhere you have to use a hypothesis of the case. U doesn't matter.
Oh.
Right.
If I draw the Dulmage-Mendelsohn barrier on the right side, I'm thinking that this is redundant because we are using only this one. But it may happen that is on the other side as
That is adjustment of notation.
Yeah.
So you need on both sides.
Both these conditions.
Yes. Okay. Now make a drawing. Yeah, this is in G prime. Good. Yeah. Put label U and V.
Then you can be. I cannot just see that.
No. In fact, even if it is, it will be trivial.
Trivial.
Then it won't help you.
Yes.
So see if you can directly make a non-trivial one.
You can be adjusting somewhat in some outcome.
Yes.
Then it is. But if that's right, I is trivial.
If it is trivial, there's a problem. But even if it is non-trivial, why is it a barrier in G? Why is B prime a barrier in G?
And that is not here.
Because maybe two odd components, they have neighbors in both of them are adjacent to U. Right. So maybe, but you can do something. U is creating problem, so make U disappear. If something is creating problem, make it disappear. Right. So yeah. Okay. So we'll make a drawing. Right. So we'll apply. So does everybody agree with this one? Everybody is happy with this? Satisfies hypothesis of Lemma 5.5. Everybody checked it? After deleting U and V, I look at partial of x minus U. So I will keep the cut like this only. There is no point. Maybe what I will do is I will put a box around these two vertices. So now I have the graph G prime. These two vertices have been deleted. That is one reason I put them on the top. Okay. So now what I have is an even cut. Earlier this was an odd cut. Now this is an even cut in G prime. Yeah. And both of these are connected because yeah. So we know that both shores of this cut, partial of x minus u in G prime, are connected, and because the original cut is a tight cut in G, we also get that these edges are unmatchable. If there is a perfect matching in any such edge, then you include UV. Now you have a perfect matching in the original graph that meets the cut C in 2 or more edges, therefore 3 or more. Contradiction. Yeah. So it satisfies the hypothesis. Yeah. Therefore we can apply Lemma 5.5 and we will get a Dulmage-Mendelsohn barrier. Right. So let's write this part. By 5.5 there exists a DM barrier B prime in G prime with some properties. In particular, the whole barrier and all the odd components are either contained in X or in X minus U, or in X bar minus V. Those are the two shores, right? So adjust notation so that the barrier is in the X side. This is my B prime. Let me put 3 vertices because 3 is as good as any other number. Yeah. This is my B prime Dulmage-Mendelsohn barrier in G prime. Adjust notation. So that B prime is a subset of X minus U. It will be a proper subset because all the odd components are also contained here. Yeah? Is this okay? So I have drawn it on this side. Now you have to think about what happens in the original graph G. Right? If we can conclude that B prime is a barrier in G, that would be great. Then we are basically done, except for the problem that B prime could be trivial. A trivial barrier doesn't help because every vertex is a trivial barrier, right? Nothing proved. But supposing B prime is non-trivial and you can conclude that it is a barrier in G, then you are done. So let's think about that. So now we introduce U and V back into the picture. The odd components can go down. So I want to show that in G minus B also, these should remain. In G minus B prime also, these should be odd components. The problem is, 2 of these odd components may merge if they have U as a neighbor or V as a neighbor. If V is a neighbor of both these odd components, then they could merge into a single component. But can V be a neighbor? No, because of case 1. V cannot be the problematic fellow here. We cannot be responsible for merging odd components into single component in the graph G minus B prime. But U could be the problem, right? U could have neighbors here, and now when you introduce U back into the picture, your number of odd components goes down. So this is the problem. U is the one who is creating issue, right? This is the case where U is correct, UR is not correct. Yeah, so U is the problem. Well, make the problem disappear. Throw it into the barrier. Delete U also. Now do you agree that this is still an odd component in G minus B prime plus U? If you delete B prime and U, then this is still an odd component. How can it not be an odd component? Where do all the edges go? All the edges have to go into B prime, U or V. V they can't go. U we deleted. Right? So B prime plus U is a barrier. Why? Because I still get all 3 odd components and I delete only 4 vertices. You delete k vertices, you get k minus 1 odd components, you are done. There is a k as odd component. You don't have to care where it is. It is somewhere. By parity. Right? You can't delete k vertices and get k minus 1 odd components. Right? If you delete k vertices and you get k minus 1 odd components, you have at least k odd components. Therefore, you have exactly k odd components. Right? This is a standard, very common argument in matching theory. Right? So that's it. So the claim is that B prime, B colon equal to B prime plus U is a barrier in G. And it is non-trivial because even if B prime was trivial, now this is non-trivial. We added something which was not in there. So therefore it is also non-trivial. Yeah. That's okay. It can't be there because it is a barrier. Barrier is stable. Right?
Yeah, but B prime is considered without U, right?
That's right.
Yeah.
So the point is, because we have shown that this is a barrier, it actually follows that you cannot have any edges there. It follows from the claim. Once you prove the claim, it follows that B is a stable set because the graph is matching covered.
We are going to prove that claim.
Right. But my point is the claim is already proved.
Oh.
Yeah, convince yourself. that this is a barrier. Convince yourself that every odd component of G prime minus B prime is also a component of G minus B. So that's my point. Alright, so every odd component of G prime minus B prime is a component of G minus B. See if you can prove this. Right? So the only difference is we have introduced these two vertices back. Look at this component. Where can all the edges go? In the graph G prime, all the edges go into B prime. In the graph G, they can either go into B prime, U or V. They can't go into V because of our case. They can go into U. Oh, but U has been included. Right? U has been included in B. Therefore, all the edges from this odd component have to go into B prime plus U, which is equal to B. So therefore, I will still get 3 odd components. I deleted 4 vertices. Therefore, I get a 4th odd component. And this is a barrier. Right? Yeah? Convinced? So we got a non-trivial barrier. Therefore, the graph is not bicritical. Therefore, we are done by star. Right? So, G is not bicritical. Done by star. So, this is the proof of case 1. Now we are left with case 2, which is not case 1, right? Okay, so that we can do after the break. And as I said, we may continue if required all the way to 8 p.m. We will finish the proof today. Because we may not have a second lecture this week, partly because I signed up for this maths department colloquium on Thursday, not knowing that Wednesday was going to be a holiday. So anyways, we will finish the proof, otherwise I think it will be a bit too long and we will all lose interest in it. So let's not do that. Okay, good. So let's take a 5-minute break and maybe 5-10 minutes and then we'll meet again. Yeah. And if you're having any food or beverages, please do that outside the room as per the email sent today. Yeah. Thank you.